Good morning, good afternoon, good evening. My name is Eduardo Juarez. I'm a professor at the Universidad Politécnica de Madrid, and I will present the paper Energy Consumption and Runtime Performance Optimizations Applied to Hyperspectral Imaging Cancer Detection on behalf of all the authors of the paper. Nowadays, evaluating the best architecture for an application and designing an efficient implementation is still a challenging task. Achieving well-balanced implementations that fulfill functional and non-functional requirements implies increasing development times. To solve this issue, the Y-chart design strategy reduces the productivity gap by isolating application and architecture concerns through models, merging both afterwards under a set of user-defined constraints. Modeling an application implies using a formalism to describe its behavior, abstracting it from the implementation details. This abstraction can be provided by models of computations, MOCs. Among the extensive list of available MOCs, Dataflow MOCs are a promising solution to ease the representation of the application parallelism. A Dataflow MOC models an application as a graph of functional entities, known as actors, that interchange tokens through FIFO queues. Although application structural parallelism is made evident in this way, it leaves out any potential optimizations that could exist within actors, since because of this representation they become black boxes. The drawback of considering actors as black boxes can be faced by exploiting some automatic optimization techniques, such as those offered by the polyhedral model. The polyhedral framework performs loop transformations to enhance both data locality and parallelism on compute-intensive codes. The combination of a Dataflow MOC with polyhedral transformations can potentially achieve a better design methodology. Non-functional requirements should also be considered as key performance indicators, KPIs of a system. Low-level events can help to discern how the application behaves at runtime. Hardware performance monitoring counters, PMCs, expose them from a processor execution and can be used to estimate non-functional KPIs, for instance the power or the energy consumption. In this paper, the advantages of these enhanced methodologies are demonstrated in a real scenario: the detection of human brain tumors during surgery through hyperspectral imaging, HSI. This use case is characterized by large volumes of information, complex algorithms, and tight performance requirements. HSI captures the reflectance of the objects present in a capture scene from a wide range of wavelengths, going from the infrared to the ultraviolet. Each HSI pixel is composed by the reflectance values of hundreds of spectral bands, which can be used as a signature that uniquely identifies each object appearing in the image. As far as the energy consumption monitoring concerns, in this work, an iterative Y-chart Dataflow-based design methodology to design multi-objective applications based on models is proposed. The methodology is composed of 4 blocks. First, an application deployment is obtained using a Y-chart approach. Then, a monitoring block is employed to profile the application execution.
Afterwards, the key performance indicator estimation step computes one or more KPI values. At last, the loop is closed using a multi-objective decision-making block. This methodology has been conceived to be applied either at design time or at runtime. Two tools are employed for the energy consumption monitoring methodology, Prism and Papify. Prism is an open-source Dataflow-based Y-chart prototyping tool where both application and architecture are defined through models. Papify is an automatic instrumentation and monitoring tool for dynamic data flow applications. The steps composing the design time loop are the following. Monitoring. First, both execution time and performance events are collected for each actor being executed. Second, KPI estimation. The Prism scenario has been extended to support energy consumption. Third, design space exploration. A tuning algorithm explores the design space considering both the timing and the energy information. Fourth, application development. The output of the design exploration block is the application deployment that will be generated in each iteration. As far as the runtime methodology, Spider is a runtime resource manager that has been designed to support runtime reconfiguration of data flow applications. The different blocks composing the runtime optimization loop that can be seen in the figure are: first, monitoring. Papify is used to retrieve performance information on both timing and performance monitoring counters, PMCs, for each actor. Second, KPI estimation. Timing and energy consumption are included within the characterization Spider has of the application and architecture being employed. Third, energy-aware decision-making. The Spider runtime decisions block has been modified to test different system configurations in each iteration. Fourth, application deployment. The standard Spider algorithm to generate the deployment has been employed. The Apollo polyhedral framework has been selected and extended in this work to conceive a polyhedral data flow-based Y-chart design methodology which fully integrates the data flow and polyhedral ones. This figure shows the proposal to connect the polyhedral and data flow domains where three main blocks can be highlighted. First, polyhedral data flow interface, which consists of an API to set up the communication channels between polyhedral and data flow domains. Second, data flow preparation. It collects all changes included in Apollo to make it data flow compliant. Third, polyhedral preparation. It automates the change of actor configuration from the data flow domain to the polyhedral environment conditioned to the activation of the Apollo tool.
To validate the methodologies previously presented, 3 experiments have been conducted. In all experiments, a common application has been used, whose main objective is to discern between healthy and tumorous tissues using HSI technology. The processing chain block that has been selected is the one in charge of classifying, by means of a supervised learning technique, hyperspectral images. The supervised learning block takes the input hyperspectral image and analyzes it in parallel using 2 algorithms, a principal component analysis, PCA, and a support vector machine, SVM, generating a one-band representation of the image and a preliminary classification of it, respectively. These results are then combined through a k-nearest neighbors (KNN) filtering algorithm to obtain a refined classification map. For the energy consumption monitoring methodologies, The selected platform is a many-core architecture, the MPPA 256. This multiprocessor system on chip is composed of 256 processing elements distributed among 16 compute clusters. The average power consumption is 15 watts. For the polyhedral data flow methodology, two different hardware architectures have been used. First, Namaka, a general-purpose multicore architecture with 16 cores running at 3.4 GHz. The RAM size in this case is 32 GB. And second, Margaret, a cluster composed of 68 nodes, each one gathering two processors with 20 cores running at 2.1 GHz. The RAM size is 192 GB. The experiments have been conducted on the 20 cores of one processor with 4 GB of RAM per core. Two images with different spatial resolutions have been selected to assess all methodologies. Regarding the validation of the energy consumption monitoring methodologies, three different working modes, fast, normal, and slow, F, N, and S, have been considered to allow different levels of MPPA resource activity, which translate into different performance requirements. The figure to the right shows the outputs of each of the algorithms of the processing chain. First, an RGB representation of the hyperspectral image is presented. Then, the one-band PCA representation of each image is collected. Finally, color maps are used to graphically represent the tissues classifying the scene in both SVM and KNN algorithms. Healthy tissue is represented in green. Tumorous tissue is displayed in red. Hypervascularized tissue is depicted in blue, and background or others are associated to black. In this experiment, the implementation obtained using the design time energy-aware optimization loop is compared with a system implemented totally by hand. The measured performance and power values are shown in the table for each combination of hyperspectral images, brain 1 and brain 2, and working modes, fast, normal, and slow. Besides, the power savings column expresses the power reduction percentage obtained with the design time optimization loop with regard to the implementation by hand. For brain 1F, power savings are not shown because the performance objective is not reached in this case. Analyzing the results, it can be concluded that the more relaxed the performance objective is, slow working mode, the larger energy consumption savings are obtained. Specifically, thanks to the energy-aware optimization loop implemented within Prism, energy savings up to 24% in a slow working mode can be achieved following an automatic system generation. In this experiment, the implementation done by hand is compared with those selected by the runtime energy-aware optimization loop on the MPPA. These results are gathered in the table where measured performance in images per second and power consumption in watts are displayed for each type of implementation and experiment. The power savings column indicates the power reduction in percentage obtained by the runtime energy-aware implementation compared to the implementation by hand. Like the previous experiment, for brain 1F, power savings are not shown because the performance objective is not reached in this case. As can be seen in the table, the power savings range from 5.81% in brain 2F to 25.67% in brain 1S. In this experiment, the sequential version of the supervised classification stage is compared to 1. P-par, which explores the structural parallelism through Prism, 2. A-par, which assesses the potential of Apollo to parallelize this application, and 3. C-par, which analyzes the combination of both frameworks. The parallelization potential is assessed using the Namaka N and Margaret M architectures with 16 and 20 processing elements respectively. The table to the left shows the execution times measured for the sequential implementation, while the table to the right collects the execution times for P-par, A-par, and C-par and provides the speedups of each tool when compared to the sequential time for each combination of hyperspectral images, Brain 1, Brain 2, and architectures, Namaka N and Margaret M. As can be seen, C-part is the configuration achieving the largest speedups regardless of the input image and the target architecture. This configuration is successful in improving the performance results provided by P-part in both architectures. C-part takes advantage of the parallelization possibilities of Prism, letting it parallelize actors that cannot be targeted by Apollo, while improving the results obtained by Prism in those actors that can benefit from the polyhedral optimizations done by Apollo. As conclusions, first, this work proposes a wide-chart Dataflow-based design methodology whose aim is to include energy consumption within the non-functional requirements to be optimized. Secondly, to further optimize applications in terms of throughput, the process of parallelizing and deploying onto multicore architectures has been simplified, combining a wide-chart Dataflow-based design with the optimization potential offered by the polyhedral model. As far as the energy consumption concerns, two real implementations of the energy-aware optimization loop have been carried out. One, targeting design time DSC enhancement, and the other focused on runtime energy consumption optimization. Promising results have been obtained in both cases, since they have been able to reduce the system energy consumption in up to a 25.7%. With regard to the runtime performance optimization, the runtime manager of a widely used polyhedral tool has been extended to evaluate several optimizing transformations and choose the best one depending on the application context. The results obtained show that the largest speedups are reached when combining the optimization potential of Dataflow and polyhedral tools with speedups close to 4 times when compared to the sequential version. That's all from my side. Thank you very much for your attention, and please do not hesitate to write me an email to eduardo.juarez@upm.es if you have any doubt or need further clarifications.